Okay, Finite Mathematics, Chapter 7, Section 2, Linear Programming, the Graphical Model. There are a few terms you need to be aware of. The first is optimal value. The optimal value of a problem is the maximum or minimum desired value. Which you want depends on the problem. If you're dealing with revenue, then your optimal value would be a maximum. However, if you were working on cost, then you would want your optimal value to be at a minimum. Another word is constraints, and these are going to be the things that limit what our optimal value can be. In the business world, these could be transportation costs, availability of materials, interest rates, a number of different things that can limit the choices that you have for your optimal value. Linear programming is used to find the optimal value within a given set of constraints. The function that we're going to optimize is called our objective function, and it will always be a linear equation. The constraints will be linear inequalities, so they're going to be the greater than and the less than. And this is why in our first section we were working with finding the regions for inequalities on a graph. Okay, we're going to start with the graphical model. Let's say we want to maximize or minimize z equals 2x plus 5y. So that's our objective function. Our constraints are what you see on the screen. Negative 2x plus 4y has got to be less than or equal to 8. 3x plus 2y has got to be less than or equal to 6. X plus y must be greater than or equal to 1. And x and y must both be positive. The first thing we're going to do is find the feasible region for the system of inequalities or the constraints. This is just what we were doing in section 1. Okay, so we find our feasible region. Here you see it. Okay. Okay, now that we found our region for our x and y values, we need to consider the objective function. Z can be anything, and whatever z is going to affect what x and y will be. And we need to find the maximum and minimum value of z, and we need to find the x and y's that will give us that. Okay, so a few examples here. If z is 0, and then our equation will look like 0 equals 2x plus 5y. If z is 5, it'll be 5 equals 2x plus 5y, and so on. If you look at these equations, you will note one thing. They all are going to have the same slope. If you solve for it, you're going to find that the slope is negative 2/5. In fact, any of the possible lines that you could create for all the different values of z you could use will have the same slope. And as we remember from geometry, lines that have the same slope are all parallel. So here we've got our feasible region, and we have a series of parallel lines formed by our equations going across it. Now some of these cross through our feasible region, some do not. The ones that are not inside the region are going to be discarded because our answers for x and y, our values must come from inside that region. Now when we look at the graph, the maximum value of z we see has to be between 10 and 15. In fact, it looks like the maximum value is going to be where 3x plus 2y equals 6 and where negative 2x plus 4y equals 8 meet. Two of our constraints where they meet, and that's going to be at 0.5 and 2.25. If you put those into your objective function and solve for z, you get 12.25. Again, if you look back at the graph, the minimum occurs at 1, 0, and putting those numbers into the equation gives us a z of 2. Now again, if you will look back at the graph, you'll notice that both of these values occur at corner points. Corner points are the points in the feasible region where the boundary lines of two constraints cross. Now, if our region is completely enclosed by boundary lines like the last one, it is called bounded. Linear programming problems with bounded regions will always have solutions. In other words, if your region is completely bounded, there will be a maximum and there will be a minimum, at least one of each. If a region is missing a boundary on any side, it is unbounded, and you may not be able to find a maximum or minimum. It just depends on which boundary is missing. Here we have 3 examples of regions. The first one, the minimum value for the lines would occur at point Q, and the maximum at point P. Our next one is also bounded, and our minimum is at point Q, but you'll notice that our maximum is actually at points P1 and P2. In fact, it lies on every point that goes in between them. So this function here actually has multiple maximum values. And then finally, our last region, we're missing a line. It's unbounded. Now we can find a minimum for that, and that'll occur at point Q, but there is no maximum value because there's no boundary. Okay, the corner point theorem says that if the feasible region is bounded, then the objective function has both a maximum and minimum value, and each occurs at one or more corner points. If the feasible region is unbounded, the objective function may not have a maximum or minimum, but if it exists, it will occur at one or more corner points. So according to this theorem, if we find the corners of the feasible region, we can place the x and y values of those points into the objective function and determine maximum and minimum values for z. And it is, again, possible to have more than one point give us the maximum and minimum values. So here are our steps for solving linear programming problems graphically. First, write down what you have. Write your objective function and your constraints. Secondly, graph the feasible region. Third, you're going to determine the coordinates of the corners. Fourth, you're going to find the value of the objective function at each corner point. You will put each x and y value into the objective function and find the z value. Next, if the feasible region is bounded, the solution is given by the corner point producing the optimum value for the objective function. In other words, once you've put all of the points into the objective function, you look and see what numbers will be your maximum and your minimum if it's bounded. If it's unbounded in the first quadrant and both coefficients of the objective are positive, then the minimum value of the objective function occurs at a corner point and there is no maximum. So let's try this. We're going to sketch the feasible region for the set of constraints, and then we're going to find both maximum and minimum values of the objective function. All right, why don't you pause this recording and give this a try, and then resume the recording and see how you did. Okay, there's a lot squeezed onto this screen, so I apologize for that. But on the left, we have our preliminary steps. We sketch the graph, and then we solve for the points where the lines meet, where the corner points are. Okay, so we have what the whole region looks like. We have a graphing calculator screen that shows somebody finding the intersection there at 6,4. It doesn't actually have all of the constraints because drawing a vertical line on the graph is graphing calculator is very tricky. So you don't have the line x equals 3 on there. But we found the corner points. If you look to the right of the screen, we see a table there. The corner points are listed. And then next to that, we have put those points into the objective function and solved. And our lowest value is 19, and that will be our minimum. Our highest value is 49, and that will be the maximum. So the minimum value occurs at 3,2, and the maximum value occurs at 512. All right, now you've gone through one, try another one. Pause the recording, give this a try. Resume the recording to check your answer. Again, here's our feasible region, and we found our corner points. Put the corner points into a table, solve for the minimum value, and that minimum value for z is 2, and it occurs at the point 2, 0. Now try this one. Again, we're minimizing. Pause the recording, give it a try, resume the recording to check your answer. Okay, here we go. There's our feasible region. And putting the 3 corner points in, we find that we actually have multiple minimum values. The minimum value will be 20. Occurs at 2, 4, and at 10, 0, which are 2 corner points, but it's actually going to occur at all the points that lie in between them. So there's actually an infinite number of x, y values that will give you the minimum value for z for this problem. All right, the rest of these problems are some examples to try. As you go through them, pause the recording, give them a try, resume the recording to check your answer, and do that for the rest of the video.